Hi folks, we are back with the first video for Unit 3, Day 3. We're going to extend what we did with the vector and parametric equations of lines to start talking about vector and parametric equations of planes. So we're no longer just looking at the equation of a line in R2 or R3. We want to be able to define a plane and be able to find any point on the plane given our equations that we're going to create. So we did talk a little bit about planes in previous units. Remember that planes are flat surfaces that extend infinitely in all directions. We're going to represent a plane using a parallelogram. So we obviously can't draw an infinite flat surface, but if we had our kind of axes in R3 here, we're going to be able to represent a plane using a parallelogram shape. So that's how we kind of draw them to show that they are going to be representing a plane like that. So this surface, we know a plane is infinite. It would continue out in all directions, but we are just going to kind of draw it as a defined, oops, that's X. We're going to draw it as a defined shape using that parallelogram. Unlike a line where we draw a straight line but put arrows on the end to show it's continuing off, that's not really feasible, I guess. Like, there's no way of like drawing little arrows all over here. But we just kind of realize and know that this shaded plane does represent kind of a continued flat surface that would continue out in all directions. And we use the symbol pi for planes. If you have multiple planes, you might denote that pi 1, pi 2, pi 3, like that. So if you see a variable of pi with a subscript, that just means that the equation following that is going to be the equation of a plane. Obviously, just a reminder here, lines are one-dimensional and planes are two-dimensional. So lines have one direction. We only need, dimensions kind of means that the directions that they can go. We only need one direction vector for a line, because any point on that line, once you've got the position from the first piece of the vector equation, you can do any scalar multiple of that single direction vector and get to any point on the line. It just goes back and forth as a scalar multiple of a direction vector. Because planes are two-dimensional, we're going to need two direction vectors. So for our plane, we're going to need two vectors that are going to form the basis of a plane. And we have talked about that earlier. Remember that those could not be collinear, and any two non-collinear vectors would form the basis for a plane. So I'm going to draw vector A on my plane and another vector B. So they don't have to be at 90 degrees, they don't have to be at a certain angle, but they just have to not be collinear and both lie on the plane. So I can get anywhere on that green plane using a linear combination of vector A and B. So we can get from any point on the plane to any other point on the plane by adding some scalar multiples of these two vectors. Like the vector equation of a line, we're first going to need to get to the plane. So we have to find a point on the plane, and then we're going to use that to find a linear combination of these direction vectors that will get us to any other point on that plane. So here I'm going to have my position vector, like before, that gets to the plane. But now, because a plane is a two-dimensional shape, we need two direction vectors to move around on the plane. Like in lines, we had a position vector to get to the line and then a direction vector that helped us move along the line. Here, we're going to have a position vector to get to the plane, but then because planes are two-dimensional, we need two direction vectors to move around anywhere on the plane. And that's how we're going to build the vector equations for planes. So I'm just going to kind of redraw that for lines. For a line, we had to get a position vector and then some scalar multiple of a direction vector. And planes are going to be very, very similar, but we won't just be able to get to the object, the line or the plane, and move in one direction or a scalar multiple of this back and forth. We have to be able to move along that single direction, but also another direction. So like I did in the previous diagram, we're going to need two different direction vectors there. So here, the general equation of a plane is going to be any point on the plane will equal the position vector plus we're going to have two different parameters. So here we have to first get to the plane. And then the direction vectors, we need both of them, A and B. This will help us move around on the plane. So any vector on a plane can be written as a linear combination. That's what this is. S times one direction plus direction vector plus T times the other direction vector. So this will let us have any vector that's on the plane. So we're going to get to the plane, and then this combination, any vector on the plane, can be written as this linear combination of two vectors. And again, those two direction vectors may not be scalar multiples. Otherwise, you're just moving in a straight line. So S times vector A plus T times vector B gives any vector on the plane. And again, A cannot equal K times B. They cannot be collinear vectors, or else this just won't work. So that is going to kind of loop back to what we talked about earlier with how two non-collinear vectors could form the basis of a plane. And that's what these vectors are doing. But we also need to know the location of the plane. Remember how in the first 2 units I said over and over, vectors have magnitude, they have direction, but they don't have location. This is now lines and planes do have a location. So that's why we need this position vector to get us to the correct location as a starting point. Then we can use our direction vectors and move around on the line or on the plane. So kind of more formalized here without just writing it all in words. So here I've got my position and 2 direction vectors. So position vector here is getting to the plane. And then 2 direction vectors. 2 non-collinear direction vectors. So again, I don't want you to have to memorize this. Just remember that I have to get to the plane and then I have to move in 2 different directions along the plane. And then piece that together. So this would be a specific point on the plane, a vector going from the origin to that point, and then A and B are going to be 2 vectors that lie flat on the plane. So the symbols we're going to use X, Y, and Z for the general point, X naught, Y naught, and Z naught for the initial position, and then A1, 2, and 3, B1, 2, and 3 for your components of your direction vectors. So again, we're going to be able to break these apart into the parametric form just by pulling apart the individual equations and having an X equals, Y equals, and Z equals. Again, I don't memorize like where each piece goes or in terms of like A1, A2, A3. I just look at the vector equation and take all the X pieces out and make one equation. Take all the Y pieces and make another equation like that. Okay, just a little note that we're now going to have 2 parameters, S and T, are typically used because that plane is 2-dimensional. So just let me hop back to this. I didn't point that out. We're going to have to declare both of those parameters as real numbers when we create our equations. So that gets us to any point on the plane. Now, in general, we can come up with the equation for a plane given different information. If we have a line and a point that's not on the line. So let's draw that out. So we've got to have a line, you need to have a point, right? We have a position. And we have a direction vector on the line. We've got that direction vector there. And if we know another point that's not on the line, like a point out there, remember that we need a position and 2 direction vectors. So if we're trying to form the plane that this line and that red point are both on, we know that this direction vector is going to be on the line there. So I could call that my A, right? I know that I already have a point. So I have like a vector going from the origin and I have an R naught. And then I just need one more direction vector on kind of using this information. So I know this point that's on the line and I know the other point. So I'm going to connect those and just make that my second direction vector. So I would just have to find my second direction vector using the point that's on the line and the other point that you're given. Okay. So use position and one direction from the line. And find the second direction. So find the second direction vector from point on line and other given point. So that's kind of the process for there. So there's 4 different kinds of types of information you could be given and have to find the equation of a plane from. Okay. You could also be given 3 non-collinear points. So I might be given point A, point B, and point C. So any 3 points, if they're not collinear, they will form the basis for a plane. And if you want a kind of visual of this, if you try and hold up a piece of paper and kind of create a plane, if you were just using 2 points, pretend this paper is flatter. If I was just holding it by 2 points, then there could be a lot of different planes because it could tilt any way. But if I added a 3rd fixed point, like there, it could only sit on top of those like 1, 2, 3 points in one way. So this will form a plane. And remember, we need a position and 2 direction vectors. So we can do this in a lot of different ways. We can choose any of the points as my position. So maybe I'll pick R0. Often people kind of pick the first point. It doesn't really matter though. And then 2 direction vectors. Maybe you pick A and B. So this one I think people kind of see fairly intuitively. So you're going to choose any point for your position. And choose any 2 pairs to find the 2 direction vectors. Like you absolutely could have picked point C as your position and then vector A, B, and B, C. It doesn't matter which order you choose those. Again, there's going to be lots of possible correct solutions for these equations. So these equations of a plane are definitely not unique. They can have any point on the plane, and we know that there's an infinite number of possibilities of those points, along with any 2 vectors on the plane, also an infinite possibilities for each of those. We can also create 2, if we have 2 intersecting lines. So here, if we're given 2 lines that cross, that do come to a point of intersection in R3, and we're going to talk more in the coming days about how or if pairs of lines might intersect. But for now, let's just say that these ones would intersect. And here, for each line, you're going to have a position. This is almost the easiest case because for each line, you have a position and a direction. So you've got a position and a direction for each one. Let's say that's my position for the second line. So here I see I have 2 positions, position vectors being from the origin to those points. Let's just pretend the origin's down here and sketch that in there. So I have 2 different position vectors and 2 different direction vectors. I only need 1 position and both of these direction vectors. So I would choose either position vector and use both direction vectors. So the direction vectors from the 2 lines. That's almost the easiest case. There's no calculations at all. You just have to kind of know the information to pick out, I would pick one of the points from one line and both of the direction vectors of the line, and just plop those into the equation for the plane. So intersecting, we would be able to see not parallel. Direction vectors are not scalar multiples. The last case is a little bit more work, and it can look kind of similar to that one, but here they are parallel, so the direction vectors would be scalar multiples. But two parallel lines can create a plane for sure. If you held up like two rulers or two pens, or two any straight objects, that would create something where you could support a flat two-dimensional surface on it. So here, I'm going to try not to mess up my color coding too much. Each of these parallel lines will have a point. Make sure I can have that in view. A point and a direction. So remember that these direction vectors are going to be scalar multiples because the lines are parallel, but I want to make sure that I draw them like very much not the same vector. So I'm just going to draw that one super little. Here, I can't use both of these direction vectors because they're parallel. They don't form the basis for a plane. So parallel direction vectors don't form the basis for a plane. I can't use both of those direction vectors, the blue one and the purple one. I can't. I have two position vectors, so I have good choice there. I can choose either point. For position. And I can use one of these two. I can use blue or purple, but not both. Oh, I almost wrote blue or purple. Choose one direction vector. But I need another direction vector. And the way I'm going to do that, maybe you guys can hear what's coming, hopefully. I have 2 points. These points are both on the plane. So I have to make another direction vector from the 2 points. So I'm going to create the second direction vector from the 2 points on each line. So kind of recognizing if you're given 2 lines, it could be either one of these 2 cases, but it's important to watch out for if those lines are parallel and recognize that you can't just use both of those direction vectors if they're scalar multiples. You have to create a different direction vector going in another direction using the 2 points, one from each line.